done, for example, for vegetation is biomass estimation or vegetation volume estimation. Because since you have a device with the capacity to see through vegetation, you can use an X-band system to get a 3D profile of the top of the canopy. We will see shortly that radar, unlike optical data, with radar you can quite easily obtain 3D information about the object. It's also surprising for something which is related with shape. Okay, let me point this out. So since you can get a 3D profile using radar data, you can use, for example, X-band data to get the profile of the top of the canopies. And then if you do the same acquisition with L-band, which tends to penetrate far more into the vegetation, down to the soil, which lies beneath the vegetation, you can get a profile of the soil beneath, and then by difference, you can obtain the height of the trees. Okay, this is one of the possible methods and one of the possible applications. But this is something that can be done much more easily with radar remote sensing than can be done with optical remote sensing. Okay. Now, having said all that, now I wanted to very briefly touch on a very important topic when you talk about radar data. And it's a phenomenon that affects any acquisition or any wave-to-matter interaction when you're using coherent illumination. So when you're using a well-defined wave, electromagnetic wave, which impacts, which hits a surface. This is something that can be seen. So let me give you an example of speckled noise. It's called salt and pepper noise because you have in the visual rendition, remember the island that we have seen earlier. Remember that the bright area was actually not all bright, but it was composed of a number of bright pixels, but then also a number of dark pixels. That's due to noise, speckled noise, which is what we are going to see very briefly now. And let me give you an example of speckled noise in the optical domain. Can you see it? Can you see that the light, I mean, if I shoot there, up there, you will see one very bright red point. So you expect that if I do a hack like this, so I take the point and I turn the surface such that the point will be spread out, you expect a bright line, right? But what you get is not actually a solid bright line. Let me show you. I will pass by. See, it's not solid. It looks like it's, yeah, spotted. So I don't want to harm anyone with the laser, but see, can you notice that it's very patchy, very spotty, right? So can you notice that? It's not solid, not at all. What you're seeing here is speckled noise. It's the same nature of the phenomenon that made you see the side of the volcano, all composed of bright and dark pixels. Why is that? Why did we see bright and dark spots, both here on the sheet of paper and in the radar image? What do these two things, what does our own acquisition here and the radar acquisition have in common? The fact that its illumination is coherent. So it's one well-defined wave that we are throwing on the observed object. this is very different with respect to natural illumination, because natural illumination, sunlight, as I said before, it's chaotic. It pours on the observed area a number of diverse waves, each one with a different phase, which all in all average to a stable response. Okay, so when we look at a scene, when I look at the scene I have in front of me, I don't see it spotty or patchy. I see a stable figure of each one of you. Why? Because not only the sunlight, but also these lamps send out light which is chaotic in terms of phase, meaning that each one of the waves may have its own phase, but they average out to something stable. When I use laser, I'm using a coherent source of light. I am throwing out one specific wave at a specific wavelength. It's also written here. It's 632 nanometers. It's red, okay? And that is coherent. I have one wave. Why does that change the game? That changes the game because if you think of a radar pixel, in a radar pixel we have, especially if we have a rough surface, like the vegetated area that we saw before, we have many points where backscattering may take place. For example, for vegetation, we have leaves. Each individual leaf can give its own small contribution to backscatter. The result is that you have multiple responses to the illuminating wave. This can also be the sheet of paper, where these are the small bumps on the surface of the paper, which each of them causes a reflection of the light. What happens there is that each one of these responses is a copy of this wave, right? It's reflected, it's a copy. And that copy, if this is one single well-defined wave, even copies will be single well-defined copies of the wave, will be single well-defined waves. Have you had to do with waves in your previous education or your previous research projects or whatever? Any of you has never worked with waves, not during education, nothing? No. Sorry? Any type of wave, as long as you're talking about a sine wave. So you may remember that if you sum this wave, because this is one pixel, so everything that comes from this area must be summarized into one average, to one sum divided by the area, okay? Into one sum. When I sum waves, their phase is relevant. If I take two waves that are in perfect accordance with each other in terms of location, then they will strengthen each other. Their sum will be constructive, okay? If I have multiple reflectors which will generate waves coordinated with each other, they will build up a strong response. If the location of these elementary reflectors is such that the waves will be in it's called counter phase, in opposite phase, they will kill each other. Okay, it depends on the location of these things. You see, if I pull one of these, the response will be a little bit delayed and the interaction will change. Are you with me? So, in principle, I could build a pattern which is maximally reflective by adjusting the location of these reflectors in such a way that will all reinforce each other. Or I can do the opposite and adjust their location in such a way that they will destroy each other. So in the first case, I will get a strong response. In the second case, I will get a weak response. But practically, I have no control over their location, right? So what happens is they are where they are, and consequently, the response will be either weak or strong or whatever case in between randomly, at least to me, randomly, right? You can make no prediction. If you are acquiring a certain area, you don't know what is there. You cannot foresee in advance what is going to happen here. And so you will get a response that you can call random. When I showed you this phenomenon here, that's exactly what we have witnessed. We don't know where the small bumps on the paper surface are located. We just see that some of them are such that the combination of reflected waves will build a bright point. Some others will be in such a configuration that they will kill, that the reflected waves will kill each other, and we see a dark spot randomly. Okay, on average, we have bright and dark spots next to each other, but each one of them will have its own behavior. This is speckle noise, and it manifests both here and in radar images. And this is something we need to live with. It's something that cannot be decoupled from radar acquisition. So, and it's one of the main reasons why you cannot rely on the individual pixel when you do radar. So what's the difference with respect to optical data? Optical measurements are stable. They can be affected by errors, but it's not the individual pixel which is affected by error. It's the data set on average. In this case, it's the individual pixel which is affected by an unknown error, and there's no way you can predict it. So if you take it as it is, you can say this measurement is meaningless. Because if I measure something which is then plagued by an error, which can be big, and which I cannot predict in advance, then what can I do with it? Now, the point is that actually there's something you can do about it. And so scientists have developed a so-called speckle noise model, which I don't want to bother you about. But the basic concept here is that you can describe this phenomenon. You can describe it statistically. Okay? You can come up with I will spare you all the formulas, but the basic concept, if I can come up with a model which gives me, for this random phenomenon, I assume you're familiar at least with the basics of probability computation or probability definition and discipline. Okay, so you know what a probability what a PDF is. Okay, so I have a random phenomenon, and it can theoretically derive its PDF, and this PDF contains the information I'm seeking. Because the idea is, I'm looking at a random phenomenon, but the random phenomenon is not fully random. It can still be described by a probability density function, right? And that probability density, the features of that probability density function will depend on the features of the observed objects. Specifically, if I have something which is very reflective, if the elementary reflectors are very reflective, I will have a PDF which is spread out. If reflectors are not very reflective or are almost not reflective at all, I will have a PDF which is shrunk and next to 0. So the variability of the measurement depends on the strength of the backscatter given by the individual small reflector. What am I talking about here? I'm talking about something like this. So what are the individual reflectors? If you imagine, for example, a homogeneous grass cover, this is one individual reflector. One blade of grass is an individual reflector. There are many, each of them giving its own response, okay? And they will combine into this sort of random response. But it's not the only case, because I can also have plowed soil, for example. The facets of the earth blocks which have been raised, which have been created by plowing, these are all individual reflectors. And one pixel is much bigger, so they will combine into one response and will cause that phenomenon. Take vegetation, leaves, rocky soil, each rock will reflect, etc., etc. But they will not all reflect in the same way. I can expect strong reflections from this. I can expect weaker reflection from this. I can expect quite strong from this. Where does this information end up? Okay, so I start from a different situation, and I want to identify the situation. So where does this information, the fact that this is soil and this is vegetation, where does it end up? It ends up here. The distribution of the PDF, because if I have strong reflectors like the clothes of Earth, then the individual reflections may sum up on, to each other to build a very strong reflection. But the same is very unlikely to happen with small leaves or with small rocks. So it's more likely to be like this. This is to say that if I want to distinguish, for example, between plowed soil and thin vegetation, I have to look here. Now, what's the problem? What is the problem that you see here? I already mentioned that. Just make up your mind and pull it back to your attention. What is the problem? I mean, this is very interesting. I have one type of soil, another type of land cover, another type of land cover, another type of land cover, very clearly defined, okay? Very clearly modeled. But why can't I leverage it? What do you have at your disposal? When you look at a pixel and you want to know whether that pixel is a vegetation pixel, or it's a soil pixel, or it's a rock pixel, what do you have at your disposal? One pixel, one sample of a statistical distribution. One sample. It's not much. So you have one sample, and that sample can be part of this, or it can be part of this, or it can be part of this distribution. You don't know. So back again to square zero. I only have one pixel. I have one element of a statistical distribution. I cannot rely on that one sample. When I have a radar acquisition, I cannot rely, in general, I cannot rely on one single pixel. What am I supposed to do then? Well, try and identify the distribution. So take a statistical approach. See the point that I mentioned this morning. You take a statistical approach. You look, you try to put together a distribution of samples. How do you do that? Well, there are various ways of doing so. One of the possible approaches is that of looking, if we go back to the image here. Why are you capable of telling me that this is an urban area and this is a rural area and this is sea? This is water. What is in the image that tells your brain that these are different objects? Not, sorry? Yeah, but that's a physics. But I'm talking about perception here. The pattern, yeah. What do you mean? Let's be more specific about the pattern. No, I'm not. What is the difference? Somehow we're getting closer. If I take a neighborhood here, what values do I find? High value, not the individual one, okay? I can find individual values that are both low and high, the individual values. But if I look at the distribution in a neighborhood, I will find that this distribution weighs toward higher values. If I take a neighborhood here, I find, even there, I find bright and dark pixels. So I find high and low values. But the center of weight of the distribution weighs toward lower values. Okay, so the individual pixel, so I'm somehow getting closer to a model. I don't have a model, but I can try and fit one of the known models on the distribution that I am observing locally. And obviously, the assumption that I am implicitly making is that I'm looking at an homogeneous area. So it cannot be too big. Otherwise, I'm introducing an error. Does that make sense to you? So when I want to classify, when I want to understand what is there in a radar image, I typically have to look at a local distribution of values, not single values, as I used to do with optical data. Let me see, wrap this up. Where could I find information on the object in optical data? I remember the filing cabinet. You pull out a drawer and you find a string of numbers. That string of numbers tells you what material you're looking at, right? It's called, what type of information? It's called spectral information, right? And even the single pixel will tell you something, because you know that there's an error, but it's generally not too big, okay? And so even with a certain margin of error, you will be able to tell this is concrete, this is metal, this is whatever. Coffee, this is coffee. And, but think of radar data. You access the filing cabinet, you pull the drawer, and there's one single poor number. Say, this number cannot do much for you. It's one number. Okay, so it cannot, for sure, it cannot distinguish materials. It cannot do much. Okay, so what you start doing is, okay, one drawer, but now let me have a look at the other drawers around here. I pull them off, and I look at the numbers in them, and I see how they distribute. Okay, it can be like, I'm making stupid examples, but just for really trying to pass the concept. It's 9, so 3 times 3, 9 pixels, okay? If I look at how these values are distributed, I can understand whether it's a very reflective or less reflective surface. And I can only see that once I access multiple samples. And I can do, in doing this operation, you may notice that I'm implicitly assuming that all these 9 pixels belong to the same class, which means that I will commit some mistakes at the edge between one line cover class and the other, because there the distribution will be hybrid. And I cannot fit a pure distribution, or a pure distribution doesn't fit well on an hybrid one. So I can expect mistakes. But here, it's very, so the human vision system, which is very clever at understanding even distribution, even local distribution, will tell you, it cannot quantify, because our brain is not designed to quantify things. It's designed to perceive the qualities. But if you look at the image with your own visual system, you can easily see that this is something that ends here, and here something else is starting. Why? Because I say, if you use an algorithm, you use something very stupid. It just takes numbers and crunches them. But if you use our own visual system, it can easily adapt, and it can suggest you what are the boundaries of the various homogeneous areas. So this is how you most commonly face the problem of classification, of land cover classification in radar data. Since you cannot rely on the single pixel, you rely on distribution. Then there may be more or less refined. There's a vast literature on that. A more or less refined way of defining the boundaries of the area that you're considering. You can have algorithms that are so smart that they realize you're trying to fit in a pure distribution on an hybrid one, so we raise a flag and say, no, you probably have to break down samples into 2 subsets, et cetera, et cetera. But the basic concept is there. Okay, it's this. So optical data, single pixel, to which you can add, if you wish, you can add spatial information, but most of the information is there. When you switch to radar data, you have you have practically almost nothing from the individual pixel. And on the other hand, you have relevant contributions from the statistics. Okay. Yeah, one last note, which is quite important. Speckle noise is not always there. Okay, so we have some good news here. When you are in a speckle noise situation, then these are the rules of the game. But you're not always in a speckle, in a so-called fully developed speckle situation. Because speckle takes place when you have land cover classes like this, a distribution of small reflectors, et cetera, et cetera. But when you have something like this is not speckle generating. When you have a building, a building is not speckle generating because it's not many small reflectors. It's one structure reflecting strongly. So the good news is that even in this image here, this is speckle noise. This is not speckle noise. This is an object. When you have something, this is especially interesting if you want to do object detection. When you have an object a single object, especially if it's a strongly reflective structure, like a trihedral structure, it's not speckle generating because you don't have many small reflectors. You have one strong reflector which kills anything else. And you look at the data set and you see that there's something here. This is the easy part of the problem. If the problem that you're facing is, I want to detect an object which has suitable features for being detected in radar data, then yes, it's there, it works, okay? Then you can move on to the next level, so understanding the features of this object, but that's a different problem. Particularly, and I mentioned this because it is relevant for the next stages, particularly if you may still be in a speckle generating situation, but if you have one item which generates a response much stronger than anything else around, then this will kill speckle noise in the sense that the speckle noise is still there, but the individual strong reflector will drag the PDF, will drag the probability density function to a point which is identifiable. Okay, so it's not, there's a random component, but there's also a deterministic component, and the deterministic component is stronger than the random component. So you're in a situation which is more similar to optical data. Strong signal plus a certain amount of error. You can live with that amount of error. Are you still with me? Okay. With the added benefit that you have amplitude and phase, which the optical data doesn't offer you. Okay. Now, how much time do we still have? 2:15 to 3:15. Wow, not much. Let me tell you a few things about interferometry. Then I will give you some more explanations in the lab session this afternoon. Interferometry. How are you doing? Because I know this is a heavy day. It's quite challenging. Are you still with me? Okay. Radar data is capable of providing 3D information, not just because it can sense shape, but because it has an inherent capability, as we have seen this morning, of measuring distances, right? It can measure distances because it can simply clock the round trip time of the wave. And this feature is very useful because, unlike for optical sensors, you cannot be too directive. The fact that you're switching to a nanometer wavelength, to a micrometer wavelength, to a centimeter wavelength carries as a consequence the fact that you cannot be too directive. You have broad images and broad listening. So you need to come up with a trick that lets you distinguish where the sensed wave comes from, because the antenna won't tell you. The antenna will put everything together. So how can you do that? The trick is, really said in a few words, is the distance measurement, is you clock. You put the sensor to one side, and then when you send out the wave, you measure the time it takes for each returning wave to do the path. So, like, let me see. No. I will try and do with this. You send a wave from an oblique direction. Remember, I told you multiple times that the observation is oblique. Now, you should see the reason why. You send a wave from an oblique direction, and the wavefront, which goes obliquely with respect to the Earth's surface, will touch the Earth's surface at one point, but then it will move on. It will continue propagating at increasing distances, right? So I don't have an animation, unfortunately, here, but it's like take the wave, and you cannot restrict it to one direction. It goes as it goes, but it takes different times to reach different places. And that's the key. When you start receiving the backscattered field, you know that at the beginning, this is the response from this side, and then increasingly from more distant places until you reach the end of the wave. So this image here, in the other direction, the mechanism is more complicated, but it's linked to the motion of the satellite. Okay, we won't discuss that. It's too complicated. But on this side, the distance, the image will be built by clocking the wave, by looking at the time it took for getting each response, and then you can use that to reproject it on the image. Okay, so why am I saying this? Because every time you get a radar data set, you also get a set of distances between the satellite and the specific location. So this suggests that if you have two viewpoints on the same object, like, for example, two consecutive orbits of the satellite. The satellite passes approximately on the same place, but not exactly on the same place. So typically, when you have two acquisitions on the same area, these two acquisitions are taken from slightly different viewpoints. So if you can measure the distance of this object from the first location and from the second location, because these two are different, it's the same orbit, but it's only approximately the same, then you can triangulate. So you can combine this distance with the location information, and you can determine the location of this point that caused the reflection. I lost you. Yes, I did. What's wrong? Why doesn't it convince you? It's something similar to stereoscopy, except I'm doing it using radar. And I'm measuring distances. So I have this satellite pass. I measure the distances, because that's the way I do in radar acquisition. Then I do the same from a different vantage point. The satellite passes here, but then the next time will pass here, which is not exactly the same place. So I measure all the distances of all the objects. I can combine these distances because the height of the profile of the object that I am observing, specifically the elevation of this point, for example, will cause a certain amount of difference between the two paths, which exactly depends on elevation. If it's higher, the two distances will be different to a different extent. Okay? Okay. So theoretically, I can do something, I can schematize it like this. One pass of the satellite, the second pass of the satellite, I can clock the distances, and from this geometric configuration, I can compute the location of this point which is being observed. But there's a big problem inherent in this approach, and it's the fact that you measure these distances with a resolution which is, well, typical of radar systems, meters or tens of meters. Tens of meters is more likely. These distances are on the order of hundreds of kilometers. Okay? And the distance between S1 and S2, between the two passes of the satellite, well, this must be in the same so-called orbital tube. So the tolerance area for the satellite pass. So it's on the order of meters or tens of meters. So this triangle is extremely thin. Extremely. Hundreds of kilometers, meters. You cannot even see it. So if you have a resolution of tens of meters on the measurement of these distances, and the displacement between them is on the order of meters, obviously, the estimation that you do of the vertical position of this point will be extremely unreliable. Does that make sense? It's extremely unreliable. You can improve it a little bit. There's a discipline which is called radargrammetry, which does exactly that. So it tries to optimize the measurement of the measurement of the height, and so you can combine different radar images to come up with a 3D representation of the area which is being imaged. But this is not, as I said, this is not extremely precise anyway. So that nowadays, what is mostly done is to use the discipline called interferometry. What is interferometry? Interferometry basically stands for using not the distance, but the phase information of the returning wave. Okay? Do not use range information because it will end up in crude approximations. So I would say the error of measurement will affect your results to a large extent. Use the phase information. Why do we expect it to be better? So the time is already exhausted. Well, let me try and get to a point where I can close safely. Sorry. I think you have seen the concept of sine wave and the phase of the sine wave. Since the phase is the displacement, as I said at the beginning, it's the displacement of the sine, the considered sine wave with respect to a certain zero, which I keep track of when I send out the radar image. When I take the returning wave and I compare it with the outgoing wave, I will find a certain displacement, which is due to distance. Because it will unfold a certain number of times, and then it will bounce back and will continue with the same pace until it gets to the antenna. So in some way, the phase of the returning wave is linked to the distance, doesn't it? Isn't it? Yes, yes, definitely it is. Definitely. So much so that I can write that the phase of the returning wave is twice, because it's a two-way path, the distance, times the exchange rate between distance and phase. What is this exchange rate? Well, I have a 2 pi phase when I walk for lambda. Okay. When I walk for lambda, the displacement is 360 degrees. And it's linear, so I can take it as a as an exchange rate. So this is very interesting. This is very interesting because building on this, not on the distance measurement using my clock, which gives me a precision of meters, tens of meters, hundreds of meters. What I'm talking about here is a precision which exceeds the size of lambda. So for an X-band system, 3 centimeters, I'm talking about a precision on the order of millimeters. What was the problem here? Remember, what was the problem here? Yep. But especially, this is relevant because you can only determine R1 and R2 to a level of precision on the order of meters, which is huge. It's much more coarse than you need. But if you consider this, instead of directly measuring the distance, if you switch to phase, then potentially you have a tool in your hand that lets you see the millimeter or even the fraction of millimeter. That's what you need. Does that make sense to you? But what is the problem? Well, there are huge problems, especially this, phase folding. Phase, by its own nature, will fold. When you get to 360, it's 0. Then you start all over again. See the problem? You start all over again. And I think, plus, it starts over again every 3 centimeters in band X. How come I can keep track of it? I'm talking about hundreds of kilometers and 3 centimeters to get back to 0. Seems impossible. But now, and here I will close this lecture. I think at this stage, you can imagine why the phase image is so messy. Why is it so messy? Because I am recording the phase. Remember, I showed you at the beginning, we have the amplitude image and we have the phase image. It means that the phase is recorded. So this variable is there. Why does it behave so poorly? Because again, I'm recording something on the order of 3 centimeters from a distance of hundreds of kilometers. It's no surprise, okay? We can call it random because basically it can be anywhere. I'm looking at something which is very far away. I'm trying to read that distance there. Obviously, it looks random. But mind, it looks random, but it is not. It's just that its variation, the tool that we are using to measure this distance is extremely unstable, okay? But the distance information is still there. So now I will, I will continue during the practical session with the explanation, but don't be scared. I think I will wrap it up in not much time, because then we will move on to the lab lecture. Okay, so it is time to close, right? Yes, more than so. So thanks again.